brings us again from the aggregate A to the aggregate B. Experiment then shows us that this change alpha prime, like the change alpha, may be corrected by a voluntary correlative movement beta prime, and that this movement beta prime corresponds to the same muscular sensations as the movement beta, which corrected alpha. This fact is usually enunciated as follows. Space is homogeneous and isotropic. We may also say that a movement which is once produced may be repeated a second and a third time, and so on, without any variation of its properties. In the first chapter, in which we discussed the nature of mathematical reasoning, we saw the importance that should be attached to the possibility of repeating the same operation indefinitely. The virtue of mathematical reasoning is due to this repetition. By means of the law of homogeneity, geometrical facts are apprehended. To be complete, to the law of homogeneity must be added a multitude of other laws, into the details of which I do not propose to enter, but which mathematicians sum up by saying that these displacements form a group. The non-Euclidean world. If geometrical space were a framework imposed on each of our representations considered individually, it would be impossible to represent to ourselves an image without this framework, and we should be quite unable to change our geometry. But this is not the case. Geometry is only the summary of the laws by which these images succeed each other. There is nothing, therefore, to prevent us from imagining a series of representations, similar in every way to our own ordinary representations, but succeeding one another according to laws which differ from those to which we are accustomed. We may thus conceive that beings whose education has taken place in a medium in which those laws would be so different might have a very different geometry from ours. Suppose, for example, a world enclosed in a large sphere and subject to the following laws. The temperature is not uniform, it is greatest at the center and gradually decreases as we move towards the circumference of the sphere, where it is absolute zero. The law of this temperature is as follows. If cap r be the radius of the sphere, and little r the distance of the point considered from the center, the absolute temperature will be proportional to cap r squared minus little r squared. Further, I shall suppose that in this world all bodies have the same coefficient of dilation, so that the linear dilation of any body is proportional to its absolute temperature. Finally, I shall assume that a body transported from one point to another of different temperature is instantaneously in thermal equilibrium with its new environment. There is nothing in these hypotheses either contradictory or unimaginable. A moving object will become smaller and smaller as it approaches the circumference of the sphere. Let us observe, in the first place, that although from the point of view of our ordinary geometry this world is finite, to its inhabitants it will appear infinite. As they approach the surface of the sphere they become colder, and at the same time smaller and smaller. The steps they take are therefore also smaller and smaller, so that they can never reach the boundary of the sphere. If to us geometry is only the study of the laws according to which invariable solids move, to these imaginary beings it will be the study of the laws of motion of solids deformed by the differences of temperature alluded to. No doubt, in our world, natural solids also experience variations of form and volume due to differences of temperature. But in laying the foundations of geometry we neglect these variations, for besides being but small they are irregular, and consequently appear to us to be accidental. In our hypothetical world this will no longer be the case. The variations will obey very simple and regular laws. On the other hand, the different solid parts of which the bodies of these inhabitants are composed will undergo the same variations of form and volume. Let me make another hypothesis. Suppose that light passes through media of different refractive indices, such that the index of refraction is inversely proportional to cap r squared minus little r squared. Under these conditions, it is clear that the rays of light will no longer be rectilinear but circular. To justify what has been said, we have to prove that certain changes in the position of external objects may be corrected by correlative movements of the beings which inhabit this imaginary world, and in such a way as to restore the primitive aggregate of the impressions experienced by these sentient beings. Suppose, for example, that an object is displaced and deformed, not like an invariable solid, but like a solid subjected to unequal dilations in exact conformity with the law of temperature assumed above. To use an abbreviation, we shall call such a movement a non-Euclidean displacement. If a sentient being be in the neighborhood of such a displacement of the object, his impressions will be modified, but by moving in a suitable manner, he may reconstruct them. For this purpose, all that is required is that the aggregate of the sentient being and the object, considered as forming a single body, shall experience one of those special displacements which I have just called non-Euclidean. This is possible if we suppose that the limbs of these beings dilate according to the same laws as the other bodies of the world they inhabit. Although from the point of view of our ordinary geometry there is a deformation of the bodies in this displacement, and although their different parts are no longer in the same relative position, nevertheless we shall see that the impressions of the sentient being remain the same as before. In fact, though the mutual distances of the different parts have varied, yet the parts which at first were in contact are still in contact. It follows that tactile impressions will be unchanged. On the other hand, from the hypothesis as to refraction and the curvature of the rays of light, visual impressions will also be unchanged. These imaginary beings will therefore be led to classify the phenomena they observe, and to distinguish among them the changes of position, which may be corrected by a voluntary correlative movement, just as we do. If they construct the geometry, it will not be like ours, which is the study of the movements of our invariable solids. It will be the study of the changes of position which they will have thus distinguished, and will be, quote, non-Euclidean displacements. And this will be non-Euclidean geometry. So we see that beings like ourselves, educated in such a world, will not have the same geometry as ours. The world of four dimensions. Just as we have pictured to ourselves a non-Euclidean world, so we may picture a world of four dimensions. The sense of light, even with one eye, together with the muscular sensations relative to the movements of the eyeball, will suffice to enable us to conceive of space of three dimensions. The images of external objects are painted on the retina, which is a plane of two dimensions. These are perspectives. But as eye and objects are movable, we see in succession different perspectives of the same body taken from different points of view. We find at the same time that the transition from one perspective to another is often accompanied by muscular sensations. If the transition from the perspective A to the perspective B, and that of the perspective A' to the perspective B' are accompanied by the same muscular sensations, we connect them as we do other operations of the same nature. Then, when we study the laws according to which these operations are combined, we see that they form a group, which has the same structure as that of the movements of invariable solids. Now, we have seen that it is from the properties of this group that we derive the idea of geometrical space and that of three dimensions. We thus understand how these perspectives gave rise to the conception of three dimensions, although each perspective is of only two dimensions, because they succeed each other according to certain laws. Well, in the same way that we draw the perspective of a three-dimensional figure on a plane, so we can draw that of a four-dimensional figure on a canvas of 3 or 2 dimensions. To a geometer this is but child's play. We can even draw several perspectives of the same figure from several different points of view. We can easily represent to ourselves these perspectives, since they are of only 3 dimensions. Imagine that the different perspectives of one and the same object to occur in succession, and that the transition from one to the other is accompanied by muscular sensations. It is understood that we shall consider 2 of these transitions as 2 operations of the same nature when they are associated with the same muscular sensations. There is nothing, then, to prevent us from imagining that these operations are combined according to any law we choose. For instance, by forming a group with the same structure as that of the movements of an invariable 4-dimensional solid. In this there is nothing that we cannot represent to ourselves, and moreover, these sensations are those which a being would experience who has a retina of 2 dimensions, and who may be displaced in space of 4 dimensions. In this sense we may say that we can represent to ourselves the 4th dimension. Conclusions. It is seen that experiment plays